Hello, everybody. I am Sci Guy Geek, and now we are beginning the fun stuff of EMag. We are getting into the first step, which is electrostatics, electric charges in a non-moving world. So everything is stationary, and we are just trying to figure out forces that these charges and charge distributions exert on each other, as well as the fields that they create. So, first thing we want to do is we want to talk about how do we define charges, and how do we define points from charges and origins. So, let's say we have a discrete set of point-like charges oriented at many different points in space, and we want to know the force that they will exert on some arbitrary point in space with some very small test charge. So we're going to call all of these source charges, all of these sources, Q, Q1, Q2, Q3, Qi, and we're going to call this test charge capital Q. So what forces do the small q's exert on the large Q? So we want to know what the force is. So first we want to start with defining the position vector between the sources and the test charge. So we are always going to define the cursive R vector from the source all the way to the position in direction of R. Now, for one charge, this is easy. For multiple charges, how do we add these together? Well, we have the idea of the principle of superposition, in that we simply add the components of each individual contribution. So the charge due to one charge, the force due to one charge added to the force due to another charge can give you the total force. So we're summing up all of these forces. So this leads us to the definition of Coulomb's law, which is 1 over r squared law, and it is given by this equation here, and it has a few major components. First is this component here, the 1 over 4 pi epsilon naught, which is simply a constant. It is a permittivity constant. And all of these values are, as the name implies, constant. So epsilon naught is the permittivity free space. In SI units, it's equal to 8.85 times 10 to the negative 12 Coulomb squared per Newton meters squared. Very simple. The next part we have are the charges. So the force is directly proportional to the size of the charges, the strength of those charges. And finally, we have the r hat over r squared term. So what this means is that the direction of the force is pointing along the direction of the line connecting the two charges. And also that the strength of this force drops off as 1 over r squared. So it is simply going, here's r, here's force, we've got this kind of slopey curve here. So that's Coulomb's law. So we defined in section 1.14, cursive r is the separation between the vector pointing to the source charges, r prime, and the vector pointing to the location of q, the test charge, q, capital Q. So we have cursive r is equal to the difference between these two values. So we can see that in this diagram here. And we have the source point is going to be r prime, so r prime here. The field point is going to be at r, and the resulting force vector is along ri. So we're going to have multiple force vectors pointing in that direction. So let's do an example. So we want to do the problem 2-1. So we have 12 equal charges Q are situated on the corners of a regular polygon, 12-sided regular polygon. So I'm just going to draw a circle, very crude circle. Actually, can I draw a better circle? I'm going to draw a circle there's got to be a way to keep this like that, and no fill. And let's see, we're going to have 1, 2, 3, 4, 5, 6, 7, 8, 7, 8, 9, 10, 11, 12. So we've got equal charges Q. So we'll call this Q1, Q2, just call this QI. So what will be the net force on capital Q? Well, we can calculate this by Coulomb's law. But let's use our intuition. We know that there is a force either pushing or pulling depending on the sign of Q, whether or not it's a positive charge or a negative charge. So there's either a push or a pull on this test charge from this one point here. Well, because these are all equal charges, we have a push or a pull coming from the other direction. It's actually in the opposite direction. It's either pulling or pushing instead of pushing or pulling. So let's say these are all positive charges and we have a positive test charge. So we are repelling this. So there's going to be a force this way from Q1 and a force this way from Q2, from Q6. So, because these are equal charges, and this charge doesn't change, these two forces are going to cancel out. Well, you can see by applying some symmetry that each of these components have an opposite component on the opposite side. So that means that the total net force is going to be equal to 0. It's going to be a 0 vector. Because remember, the force is a vector. So, now, let's go to part 2. Suppose one of the 12 Qs is removed, the one at 6 o'clock. What is the force on Q? Explain your reasoning carefully. So now, we've got nothing there. So now, what is this force on Q? So, again, assuming these are all positive, and Q is a positive test charge, there is going to be a force down. Now, like we said before, all of these 10 charges are going to have an equal and opposite pull, equal and opposite push on Q. So there is going to be no net force due to any of these charges. But there is going to be a net force in this direction. So if we had just and this is our origin, this is X, this is Y, the net force is going to be some constant alpha in the negative y hat direction. Now the strength of that force is going to be equal to alpha is going to be equal to 1 over 4 pi epsilon naught times Q, capital Q, r squared minus y hat. Actually, the way I have this written in alpha is just this. So alpha is not a constant. It is dependent on the distance r. So that was my mistake. But it is proportional to the size of the two charges and the distance between them. So, there we go. There's our first idea of electrostatics. The idea that the force due to a charge is proportional to the accumulation of all the other charges that are acting on it. Okay. So, like we said before, if we have several point charges, all at different distances from Q, the total force is given here. Well, let's see. They all have this factor of Q times 4 pi epsilon naught, so we can pull that out. And then we see that we have this Q1 over R squared R hat, Q2 over R squared, R2 squared, R2 hat, 3, 4, 5, all the way up to however many charges that we have. We can define, since this is the only vector component, we can define this as E, the electric field. So, the electric field is defined as the field of the source charges, a field that is created by the source charges. So if we put any test charge within that field, it will feel a force in the direction of that field at that point. So we end up with this equation where we sum up all of our charges so this asks us to find the electric field a distance z above the midpoint between two equal charges q, a distance d apart. So shown here. So we want to find the field at this point. Now remember, you don't need to have multiple charges to determine a field. One charge exerts its own field. Two charges combine their contribution of the field together. It's a superposition principle. So we can go through the math here. And it's a simple trigonometry method of just understanding. So this was all for static fields. Sorry. This was all for singular point charges. Well, we can extend this to a continuum of charges, continuum of static charges, some continuous distribution, either some line charge, some surface charge, or some volume charge, each with their own density of charge. So how much charge is packed within an infinitesimal element, either a line element, a surface element, or volume element. So Sandoval, hey, how you doing? Welcome in. Good to see you again. We are learning electrostatics, and we are talking about electric charge distribution right now. Missed you too. So, we have some charge. If we had some charge spread out along a line, as in here, then the charge per unit length, this dq, is equal to the density, the line density, times the length. Likewise, if we had this over a surface, it would be the surface density times the area, some dA. And if it was a volume, it would be the volume density, the volume charge density, rho, over some infinitesimal volume element. So we have three equations here. The electric field due to a line charge, surface charge, and the general form of a volume charge. So this will reduce to either one of these for the particular case. So this is the general form of Coulomb's law, where we have electrostatics. So, remember that R is the direction from the source to the test point. So, let's look at our example. And bring this up. So, find the electric field at distance z above the midpoint of a straight line segment, length 2L, that carries a uniform charge line charge lambda. So, we have this. Here we've got the x direction. We've got the z direction, and we've got this whole thing is 2L. So, first thing we want to do is define our origin. We want to define our source vector, our pointing vector, and our cursive r vector, as well as our dl. So first of all, if we define our origin as the middle of the line, then above the midpoint of a straight line segment, above the midpoint of a straight line segment. So define our origin at the midpoint, and we want to find some arbitrary point P. So, R is simply this. This is our R vector. So R, or better R, is equal to Z, Z hat, where Z is the distance to point P. Now R prime is the distance to our infinitesimal charge density. So R prime is equal to, and this is along the x-axis, so it's simply x hat. Very easy. Now, what is dl? dl is along the x-axis, and it is r dx. So, now we need to find out what our cursive R is, and our cursive R is equal to R minus R prime is equal to z hat minus x hat. The magnitude is simply square root of z squared plus x squared. So this here we go. I can draw straight lines now. This is our cursive R. With a vector going in this direction. So, what is Coulomb's law? Well, from what we saw before, Coulomb's law for a line charge to 1 over 4 pi epsilon naught times the integral of lambda. Now lambda is a, they say it is a constant uniform line charge. So lambda is not dependent on the distance r at all, divided by r cursive r squared r hat d lambda dl. Oh, sorry, dq. I was right the first time. It was dl. It's dl prime. So subbing all of this stuff in, lambda is a constant. We have E is equal to distance from negative L to L, because we're starting here and going over here. I should put out my constants. Lambda is a constant. 4 pi epsilon naught. Negative L to L of one over c squared plus x squared Now, what is r hat? Remember, r hat is simply r over simply cursive r over cursive r magnitude, and then dx, because that's what dl prime is. So, what do we got? Well, we know that our vector is this. We know our magnitude is this. So we have a z squared plus x squared times z squared plus x squared all of the square root. So if you remember your algebra, that's going to be the z squared plus x squared to the 3 halves. Remember, this can be seen as raised to the power of 1. We're multiplying powers together. So we multiplying terms adds the powers. So we get lambda 4 pi epsilon naught times integral negative L of z hat minus x hat times z squared plus x squared to the 3 halves dx. So we have two equations. Well, we have one equation, which we can now factor into two equations here. See if I can move this up here. And then, yeah. So now we have equation for z, equation for x, because remember, we integrate along x. We can break up this integral into two integrals, z hat over this term minus x hat over this term dx. So going on, this simply becomes, takes a lot longer to write it out than to actually do it. negative L over L, put a bracket. And we've got, remember ZZ hat is, I'm gonna put a bracket, Z hat negative L of 1 over Z squared plus X squared to the 3 halves. Make that a dx minus negative L X over Z squared plus X squared to the 3 halves dx. And x hat is a constant. X hat. So, there we have our integrans. And we have a simple Calc 2 problem. Now, whenever we do these types of problems, you're going to see a lot of this term pop up, this magnitude term. The either the square root of the magnitude, or the 3 halves of the root. So it's just something that you're going to have to get used to. You can either look up an integral table or simply solve it. But reducing all of this down, we get E is equal to 1 over 4 pi epsilon naught times 2 lambda L over Z root Z squared plus L squared Z hat. So this term goes to 0. Does that make sense? It should. If we look at our initial drawing, let's see if I can move that out of the way. And that out of the way. So, if we look at our initial drawing, then we see that we have, for every infinitesimal charge element on this side, we have an equal element on this side, which is going to point in that direction. So we have matching components in the x direction. So whatever component in the x direction we have has an opposite component in the opposite direction. So only thing that matters is the z component, which is exactly what we see here. So, electrostatics. First, points far away from the line. The line looks like a point charge of Q is equal to 2 lambda L. If we increase the length we have an infinite straight wire, and we see that the electric field is proportional to 1 over z. 1 over the distance squared. Sorry, 1 over the distance. So, some more complicated problems, which we can go over later if people ask. But let's go over, let's see. Let's go over another way to calculate the electric field. So, as Griffiths says, that's it for electrostatics. Basically, you have hydrate. I'll be right back. Send oval. I need to get my water. Okay. So, got my water. Thank you. So, like Griffiths says, this is basically all there is to electrostatics. You have a distribution of charges. Sorry, just electrostatics. No magnetic charges, nothing moving. You have a bunch of electric charges. I'm doing well, Game of Strongman. I'm moving to New England. Lies again. You banned that fool long ago? Well, hey. Nothing's bad's happened to me, but people on Twitch gonna be a little weird. It happens. How are you doing? Doing great. Good to hear you. So, I just got through a big problem looking at a bunch of math. Finally getting an answer for electric field. Doing great, kicking ass and taking names. Nice. Good to hear. Lifting is going well. I take it. Awesome. Awesome to hear that. Oh, 425 snatch grip deadlift tomorrow morning. Oh, jeez. Yeah, I've got deadlifts tomorrow too. I'm probably going to be doing sets of 6 at 275, 285. I'm just getting back into it, so I tried 315 and that killed me. So we'll ease back into it. But yeah, moving on. Doing well. Oh yeah, my squats are already moving pretty well. You've seen my Instagrams. Was doing 255 yesterday for sets of 6. And those felt challenging, but not difficult. Well, challenging, but not strenuous, overly strenuous. You're signing up for a comp in Peabody. Where in Peabody? Where and when? Strength Discovery Gym. I might know that area. I gotta... Yeah, but yeah, let me know when you're gonna be doing that. I've gotta make the trip over there. I've got family in the area. So, question is, do I continue on with... Let's see if I can get to the electric potential. So let's get this next section done. So we have electrostatic fields. So we want to know how these... Crush the science? Thank you for the lurk, my friend. Thank you for the lurk. Okay, so we want to know how these fields interact, how they diverge from a point, how they curl around a point, and what type of work we can get from that. So, if we have a single point charge Q at the origin, we have our equation for the electric field, Q over R squared, 4 pi epsilon naught. This is going off of equation 2.4. So, we know that the strength of the field is inversely proportional to R squared. So the strength of the field, the little arrows are going to get smaller as we go further away from them. Notice that there is no connecting of the arrows to form field lines. Okay. So, you draw these field lines, and you can say that the electric field is denser when there are more field lines in a particular region. So when they're denser, the more complicated the figure is, you can get a feel of how these charges move, or how these charges would move a test charge. So, here we have two opposite charges, and we see that field lines go from positive charges to negative charges. So this is the source, here's the sink. And we can determine the flux of E through a surface. That is, how many field lines are going through a particular surface element over an entire surface region. That is the flux. So, remember, the flux tells you how many field lines are going through a surface. So it'll tell you an idea when you enclose a surface. It will tell you how much charge is in that surface, which is very useful. So if we know a charge distribution, we can figure out the field by drawing a enclosing surface. We don't have to do Coulomb's law. Field lines that originate in a positive charge must either pass out through the surface or else terminate on the negative charge inside. Charge outside the surface will contribute nothing to the total flux, since its field lines pass in on one side and out on the other. This is figure 2b. So, these charges stay inside the volume. Everything else goes outside. There's a flux outside. But any charge outside the volume will simply just pass right through. Okay, so now let's make it quantitative. So, we've got a surface element, the flux through a surface dA, write out the Coulomb's law, and we're going to write this in spherical coordinates. So if we have the flux E through a spherical surface of radius r, here's our surface volume element for a sphere in the r hat direction. For a point charge q at the origin. So this entire integral, this whole complicated thing, is equal to 1 over epsilon naught q. So when the surface area goes up as r squared, as the field goes down in r squared, so the product is constant. In terms of field line picture, it makes good sense, since the number of field lines pass through any sphere centered at the origin, regardless of size. The number of field lines go down as we make a bigger sphere, but the surface area goes up by the same factor. And the funny thing is, it didn't have to be a sphere. This could be any closed surface, and it would equal this value here. Any closed surface. The flux through any enclosing surface is q epsilon. Now what if we had a bunch of charges? Well, the total field is going to be equal to the summation of all the individual electric components. So the surface is going to be the sum of all those components over an enclosed surface, which is going to equal the sum of all the charges, which is just the total charge enclosed within a surface. This is Gauss's law. Gauss's law is an integral equation. We have the electric field within a closed surface is equal to the total charge enclosed divided by epsilon naught. So we can turn this integral equation into a differential equation by applying the divergence theorem here. So remember, we can turn surface integrals into volume integrals, and we can turn line integrals into surface integrals. So, applying the divergence theorem, we take the divergence of E. So Q enclosed is equal to the charge density. So we have the volume of the density, charge density, is equal to the volume enclosed by the divergence of E. But this holds for any volume. So that means that these quantities must be equal. And we have the differential form of Gauss's law. This is very important. This is one of Maxwell's equations. There are 4 of them, and this is the first one we will get to. So the divergence of E is equal to the charge density divided by epsilon naught. Easy enough to find. So, more on the divergence of E. And we can do some problems for Gauss's law. But in reality, there are really only 3 problems that we can do with Gauss's law. And they all have to have some kind of symmetry. And that's in order for us to make cancellations. So let's move through and we can go through these examples or we can skip them. If people would want to, I can go back over these problems. But let's get to the curl of E. So we have our definition for a single point charge E. We want to calculate the line integral so at a glance, we drew a picture of this vector field, and we saw we just had points radiating out or radiating inward depending on the charge of Q. So if it's a positive charge, everything is going out. Negative charge, everything is going in. So what if we had a line integral from some point A to some point B, what would E dot dl be along this curve? Well, E dot dl will simply be where dl is equal to dr r hat, r d theta theta hat, r sine theta d theta d phi phi hat. So E is only in the r direction. So all of these terms cancel out. And we are left with this. E dot dl is equal to q so we see that it is only dependent on E dot dl is only dependent on the radius away from the point. Easy enough. But if we had the radius of point A equal to the radius of point B, then we can see that this is 0. So we can see that the integral around a closed path is 0. So E dot dl is equal to 0. Applying Stokes' theorem, converting a line integral into a surface integral, we can get this for any surface, and we see the differential form of the curl of E is equal to 0. So this is for a single point charge. So, but this holds for any arbitrary choice of coordinate system. So wherever the charge is located, with superposition, summing over all of these fields, we can basically just say, all right, well, the curl of E is equal to the curl of all of the electric fields that we looked at, but that's just the curl of each one individually. But the each one individually all contribute nothing. So the whole thing contributes nothing. So the curl of E, so this equation holds for any static, very important, charge distribution whatsoever. So, what did we go over today? We went over Coulomb's law, Gauss's law, and the curl of E, finding out that the curl of E is equal to 0. So, I'm going to leave it off at that. Take care, everyone. I will see you all later, and we will go over electric potential then. Take care, everyone. Hope you all have a good night. I will catch you all later.